Hey, have you ever wondered how we can truly trust machine learning systems, especially given how complex and unpredictable they can be?
Absolutely. The whole black box nature of machine learning models always gets me thinking. Even if you understand the inputs and the model's structure, it's almost impossible to figure out how it arrives at specific outputs.
Yeah, that's exactly what the issue is. These models, particularly these deep neural networks, are so complex because they rely on countless parameters and computations. Their decision making processes are hidden in layers of abstraction.
Right, right. It's like inductive learning in action. Instead of following explicit rules like traditional software, machine learning models learn patterns and relationships from data. But since those patterns are encoded in internal parameters, it's tough to trace how decisions are made.
Yeah, exactly. And then there's also the statistical nature of machine learning models. Their outputs are probabilistic and they're based on statistical inference, which means they can't always guarantee a 100% accuracy. And there's no rule book to tweak or to fix errors, unlike what you have in traditional systems.
And let's not forget the complexity of input spaces. With applications like image recognition or natural language processing, the relationships between inputs and outputs are so nonlinear and complicated that isolating the impact of single input is next to impossible.
Right. And that's also why testing these systems is always such a challenge. Traditional methods, they depend on understanding a system's internal logic, but you can't just use that method for these black box models. We don't know what the system's internal logic is like.
So, how do we deal with this?
Yeah, that's a good question, and that is exactly where probabilistically extended ontologies, or peons, come into play. It's this novel concept introduced in this paper I just read. And these peons provide a framework for testing machine learning systems without needing to pry into the inner workings of models.
Okay, that's interesting. I'm really curious. What exactly are PEONs?
Yeah, it's a big word, and don't worry, I'll break it down
Yeah.
for you. Ontologies are like these formal blueprints of knowledge for a given domain. If we're talking about something like a self driving car problem, then we can split the problem up into three different types of things. One is classes, the other is properties, and the last is relationships. So, classes are entities or concepts like persons, vehicles, road, the weather, traffic lights, and these types of things. Properties are attributes of the classes we just talked about. So, for a person, they can have attributes like age, they can have something like height, they can have something like walking speed. And for a vehicle, they could have size, they could have the speed and other things, color. And then relationships are the things that connect different entities together. So, for example, the person class is the one who's driving something from the vehicle class. So, a person drives the vehicle. A relationship is just something that connects entities.
Mm, mm, I got it. So, how do ontologies extend it into this PONs?
Yeah, so peons or probabilistically extended ontologies just take it another step further by adding probability distributions over these partitions, over these separations. So imagine we're talking or testing a pedestrian system in a city, a pedestrian detection system. The ontology might partition the input data into categories like for pedestrians, you have children, adults, the elderly. For vehicles, you have cars, trucks, bikes. For weather, you have sunny weather, rainy weather, snowy weather. And then what the peons would do would be to assign probabilities to these partitions based on how often each of them occur in real world scenarios or natural scenarios. For example, you might expect something like adults and sunny weather to be overrepresented for a certain area, whereas snowy weather and children riding bikes would be very, very underrepresented because it's just not common.
Oh, I see, I see. It's not just organizing information, but also incorporating real work likelihood, isn't it?
Yeah, exactly. And this is what lets you test machine learning models in a way that reflects natural conditions, realistic scenarios. It's a type of representative testing.
It's very interesting. Does it help define when testing is complete?
Absolutely. So peons also allow you to calculate statistically significant sample sizes that give a clear end of test criteria. They also ensure fairness by letting you specify uniform distributions for sensitive attributes like gender or race to see that they have no effect on the final model performance.
Hmm. No, that's a game changer for ethical testing. But I'm wondering, how does this approach compare to traditional software testing?
So traditional systems operate deductively. They follow an explicit set of rules which you can trace back to understand their logic. You can test traditional systems with methods like endwise testing, and this essentially just checks the combinations of different inputs. But that doesn't work for machine learning models because machine learning models are, by definition, probabilistic and inductive, not deductive.
I see. So traditional testing isn't equipped to handle the randomness or statistical nature of machine learning systems, is it?
Correct. The paper that I'm talking about also showed how NWise testing specifically fails. In one experiment on a machine learning object detection system, NWise testing could not reproduce the key quality criteria or align with the development process. It was functionally useless.
Ah, that's a pretty clear limitation. What about machine learning based testing methods themselves?
Another great question. So, machine learning based approaches offer several advantages. First, they're able to handle just the sheer complexity and scale of modern machine learning systems. They can analyze these huge, massive data sets and then generate diverse test cases from them.
Oh my goodness, that's huge for efficiency.
Definitely. And they're also good for adaptability. So as these systems evolve, the testing methods can also be adjusted to keep up. And the best thing about this maybe is that they can be automated. So you can have faster and more comprehensive testing cycles without needing a human to automate or work behind the entire process.
Actually, again, so curious. I'd like to know what about areas where traditional methods really struggle, like fairness or detecting subtle biases?
Yeah, so machine learning methods also shine in this area where traditional methods can't. Machine learning techniques can analyze outputs across many input ranges, a vast array of input ranges, to uncover any of the hidden biases or inconsistencies that a human evaluator might miss. And this type of testing can also, go over non-functional requirements like ensuring maximal fairness, explainability, and robustness of these models. And when we're analyzing a machine learning model's performance across different scenarios or partitions, as we said earlier, it can help us spot hidden biases that might not show up in the overall results. So, for example, if we're talking about a model that detects cyclists well during the daytime but struggles in the dark, this could reveal a bias in how the model handles low light conditions. We could also look for unexpected behavior, like the model being inconsistent in certain scenarios, even if it's generally accurate overall. A human evaluator might gloss over these and just miss them altogether. And that's not the case with machine learning models. By breaking down performance across these partitions, these models can uncover issues more frequently and they can improve model reliability in all kinds of different real world conditions.
And it sounds like this could solve the Oracle problem too. Traditional testing relies on having a precise expected output, which isn't always possible for machine learning systems.
Exactly. You don't really need a perfect oracle that's all knowing and all seeing. Machine learning based testing focuses on statistical behavior and deviations from expected patterns, which is sufficient for our use cases.
This is really fascinating. It feels like PONs and machine learning based testings are reshaping how we evaluate these systems.
They really are. And the paper I'm talking about also emphasized some of the ethical applications of this technology that boost fairness and remove bias, as I mentioned earlier. Looking ahead, it seems like the authors want to develop tools for creating ontologies and then use them to analyze weaknesses that currently exist in our machine learning systems.
Mm. It sounds like testing is going to be as innovative as the systems it's supposed to validate.
Yeah, I couldn't have said it better myself. With frameworks like Peons, we're getting closer to building machine learning systems that are not only effective but also trustworthy and ethical.